Okay, in this video we continue discussion on properties of cut sets of a graph. So the last video we proved this statement: every cut set in a connected graph G must contain at least one branch of every spanning tree. So in this video we are going to prove the converse of this statement. So the converse of that statement reads as follows: in any connected graph G, any minimal set of edges containing at least one branch of every spanning tree of a graph G is a cut set. So here this statement reads: every cut set in a connected graph G must contain at least one branch of every spanning tree. So this says any minimal set of edges containing at least one branch of every spanning tree is a cut set. Okay, so let's go and prove this statement. Okay, so let G be a connected graph and S be a minimal set of S be a minimal set of edges containing at least one branch of every spanning tree of G. Okay, so let and S be a minimal set of edges containing at least one branch every spanning tree every spanning tree of G. Okay, so let's look at G minus S and see what is going to happen. So here we can see that G minus S, it is going to be a subgraph of G anyway, from which at least one branch of every spanning tree is missing. Okay, so that is how we chose this C, right? S be a minimal set of edges containing at least one branch of every spanning tree of G. Okay, so let's consider this particular subgraph G minus S. Okay, it's a subgraph. Okay, it's a subgraph of G from which at least one branch edge of every spanning tree is missing. Okay, edge of every spanning tree is missing. Anyway, this is how we chose this particular S, right? S be a minimal set. Okay, S be a minimal set of edges containing at least one branch of every spanning tree of G. So G minus S is a subtree of G from which at least one branch of at least one branch of every spanning tree is missing. Okay, so that says, so this graph G minus S, it cannot contain any spanning tree of G completely, okay, because some of the edges are missing. Okay, so G minus S, it cannot contain any spanning tree of G completely. And that says this graph, it must be disconnected. So it must be disconnected. Okay, anyway, that's what we are aiming for. Okay, we want to prove that Okay, when we delete this S from this graph G, then the graph must get disconnected. okay, and any proper subset of that, okay, it won't disconnect graph. Okay, then if you are able to prove that two statement, then we can say that this is a cut set. Okay, that's what we are heading for. And now we are able to prove that, okay, G minus S, okay, it is a disconnected graph, and we have to prove that, okay, if you delete any subset, then the graph must be connected. Okay, so that's what we are going to prove. Next, again, we are going to use the property of the spanning tree kind of thing to show that one. Okay, so we proved that G minus S is disconnected. Okay, and say, so let's prove the other thing. Any proper subset of S, okay, it cannot make the graph disconnected. Okay, since S is a minimal set, okay, it's a minimal set of edges with this property. So this property means if you delete that edge, then the graph will become disconnected. Property, any edge E from S. So if you take any edge from S, so we deleted, okay, S from this graph, and if you take any edge, say E from S, and if you put that edge back here, we can see that, okay, at least one spanning tree will start appearing. Okay, so that says, okay, that graph will become connected, and that is true for any edge in this set S. Okay, so here this E is an arbitrary one. Okay, and that says any subset of this S, it won't disconnect the graph G. Okay, so since S is a minimal set of edges with this property, any edge from S added back, okay, back to this subgraph G minus S, okay, will create at least one spanning tree. Okay, so that says, okay, G minus S plus this edge added graph, okay, it will become connected. So therefore, okay, G minus S plus E, okay, this particular graph, where we reintroduce this particular edge will be a connected graph. Okay, and that says this S is a minimal set of edges whose removal from G disconnects G. Okay, and okay, that's what we want, and that satisfies the definition of a cut set, and so S is a cut set. Okay, so thus we can see that this S is a minimal set of edges whose removal from G disconnects G, and now proper subset of S, okay, doesn't disconnect. Okay, so this S, it satisfies the property for the definition of, okay, the subset being a cut set. Okay, and thus S is a cut set of G. Okay, and that's where we were heading for, and that's the theorem. Okay, and hence the theorem. So that says, So that says in any connected graph G, any minimal set of edges containing at least one branch of every spanning tree of G is a cut set. Okay, so we will look at more properties in the next few videos.